I enjoy this final part of the section where we get to talk about cool things that we can do with uniqueness. And maybe they're not that cool to you, but they're cool to me, so we'll talk about them. So we're going to start by saying that we get better qualitative analysis if we know something is unique. And so we're going to look at that with the example that we just finished the last video on. Better qualitative analysis. What do I mean by that? I mean, okay, let's look at this slope field again, a slightly different version. Sine of y squared. It has some equilibrium solutions. It has a ton of equilibrium solutions, right? Every pi k really, we have equilibrium solutions. Well, now the question is, if you remember back to, which one was it? If you remember back to this example, right? We had two solutions, t cubed and 0. And so what that looked like, right, is we had one solution that looked like a cubic and an equilibrium solution as well. And so the solution crossed the equilibrium solutions. Well, if this is unique, we know that they don't cross these lines. They're stuck between these lines. If all solutions to this ODE are unique, they're stuck between these lines. If we don't have uniqueness, then yeah, who knows? Maybe it's going to curve up and then cross and then curve up and then cross the next one and then curve up. We don't know. But uniqueness tells us whether we're stuck, which is really nice. So of course, you know that this is a continuous function. Sine of y squared is continuous. So we have the existence of a solution. And we know that the partial derivative with respect to y is also continuous. It's 2 sine y cosine y. All right. So because that's also continuous, we know we have uniqueness. Because we have uniqueness, we know solutions are trapped between each equilibrium. And of course, if you plotted it with something like this tool, right, each solution is going to be trapped between one equilibrium and the next equilibrium. All right, and that is something that we don't need this tool to graph these blue, purple, and black solutions. We know them just essentially by hand. All right, so that's kind of cool. And again, for autonomous solutions, we're going to actually make cool little graphs of these in the next section where we talk more about what we can do with autonomous differential equations. So again, yeah, that's pretty much it for the first one. The second thing, I do not want to write it like that. The second thing is that you can compare, and this is really quite similar, you can compare or bound different solutions. Because one of the ways that we can kind of think of uniqueness is, in a sense, right, uniqueness kind of means their solutions aren't going to cross each other. Because, and why is that the case, by the way? It's because of this. Right? If their solutions, essentially if they equal each other at one point, and they're unique, then they have to equal each other everywhere. And that's why they can't really cross, because it's gonna fail that part of the uniqueness conclusion. So let's look at something. Look at an example. If dy dt is equal to 1 plus t squared over 1 plus y squared, and let's say we have one initial condition where y1 is equal to 0. Let's say we can have a different initial condition. Like, well, let's look at two problems, right? Here's problem A, here's problem B. They have the same differential equation, just two different initial conditions. All right. Well, you know that y1 of t equaling just t is a solution to A. I highly recommend, I'm not going to force you to, of course, but I highly recommend you pause the video and prove that that's true. Definitely has the right initial condition. And then again, you can plug in y here. This whole thing cancels out to 1. And then you know that the derivative is also 1. All right, well, I guess you don't have to pause the video. I just did it that fast. All right. So we know that that solution solves it. And we know what this solution looks like, right? In the ty plane, right? If this is t and this is y, we know the solution to a, right? This is y1. Just the diagonal line. All right. Now we also know, what do we also know? That if we have a second initial condition of something that, I don't know, maybe it's negative 1/10. All right, and we don't know what y2 is. So maybe y2 of t equals something. And we know the initial condition is going to be like really close under here. We know because of uniqueness that this second function, which I don't know what the second function is, it's going to be more complicated. This second function is always bounded by this line, right? Because we can't have it do anything like this. Oh, because then they would cross. And we know we have uniqueness of solutions right here. Why do we know we have uniqueness of solutions? Because this is our f. I know that the partial derivative of f with respect to y, no quotient rule necessary. We're taking partial derivatives here. So this is just, we can take out everything with a t. This is just the partial derivative with respect to y of 1 plus y to the negative 2. When you take this derivative, right, you're going to get negative 2. Again, this whole thing stays in front. And you're going to get negative 2 times 1 plus y to negative 3. So it doesn't exist when y is equal to negative 1. That's an exponent of negative 3 right here. Sorry, I'm covering it. It's not continuous when y is equal to negative 1, but we don't have y equal negative 1 right here. So we do have uniqueness everywhere for t greater than 0. Because again, similarly, we know that this slope is always positive. We know dy dt is always positive, so we're never going to get to negative 1 with this initial condition. Which is a little bit more complicated than I anticipated it being, because there's really a lot of things going on here. Let me move my camera just a little bit. I don't like that I'm covering this up. Oops. All right, that was not it. But yeah, so again, just to more slowly unpack this, right? We are guaranteed uniqueness because this partial derivative is continuous for y is greater than 1. We know y is going to be greater than 1, looking at positive time, because this is always an increasing function. This can never be negative, so dy dt is never negative. Because of that, we know we have, for t greater than 0, and again, let's specify that. For t greater than 0, y will also be bigger than negative 1, which means we all have uniqueness, which means we'll never cross this line. Who knows what we're going to do? But we're not going to cross that line. We know we're always bounded. So we don't know what y2 is, but we do know that y2 is always less than or equal to y1, which was just t. So it doesn't give us a ton of information, but it gives us some information. Again, it's just more tools that we have. Having access to uniqueness just gives you more information about a function that you may or may not be able to find by hand. And yes, this is actually separable. Yes, you could actually find this by hand. It actually would not be that hard to find an implicit version of it. It might be actually kind of hard to find an explicit solution. Yeah, but you could find an implicit solution to this. That wouldn't be too bad. All right. And the last thing that we can use relates back to our numerical techniques. So if you remember back to our last section on Euler's method, we had a fun little example that we did. And I had a blast with it. We looked at Euler's method for this differential equation. It's not autonomous because it has this part, but it is separable, right? Because it's a function of t times a function of y. So it is separable. We can solve this by hand. Again, we'll get an implicit solution. We have to be very careful about dividing by 0 as well, as we saw in the last section. But anyway, if we have this where y of 0 is equal to just 5, then we had that weird, wacky situation, right, where we had the solution kind of get close to pi and then go. The dog did not like that, but that's basically what happened. if you remember. All right. Actually, let's leave that up. That's what happened. This is the actual graph of what Euler's method, not the function itself, but what Euler's method told us the function looked like. All right. Well, is that actually what the function looked like? Is that actually what the solution looked like? Well, we know the solution exists because this is a continuous function. We haven't talked too much, depending on what level of calculus you've taken, we haven't talked too much about what continuity means for multivariable functions, but suffice to say, this is continuous. All right. And the partial derivative with respect to y is also continuous, because what's the partial derivative with respect to y? Everything with a t we treat as a constant. So the partial derivative of this with respect to y is just this, which is also continuous. So we know the solution's unique. And again, remember that we said we had equilibrium solutions. We did this in the last section. We had equilibrium solutions at y is equal to pi k. Right? So y equals 0 was an equilibrium solution. Y equals pi was an equilibrium solution. And y equals 2 pi was an equilibrium solution. All right, we had all these equilibrium solutions. Well, since we have uniqueness, right, that tells us that solutions have to exist. If there was that they're unique. So this is not a possible solution. This red curve is not a possible solution because it fails uniqueness. Specifically, our initial condition was y of 0 equals 5, which is right here. So specifically, I should say, right, that I think my claim was actually fine. So the question is, right, this is what Euler's method said our answer looked like. Well, that's impossible, which you may have already guessed that wasn't correct. But now we have proof that this is impossible because it has to. We know it has to be between these two equilibrium solutions. Whatever solution looks like has to be stuck between these. Otherwise, it fails uniqueness, and we know we have uniqueness. So you might guess that the solution maybe looks like that. You might be right. We'll revisit this example later. Okay, but that's some of the power of uniqueness theorems as they relate to numerical techniques. That's pretty much it. If you're curious to why Euler's method does this, it's because this grows so fast. So your slope gets so big that you're just like vastly overshooting what is supposed to actually happen here. Okay, so I actually don't quite remember what the actual solution looks like, but it'd be fun to talk about sometime. Anyway, until next time, enjoy existence and uniqueness. The next video we talk more, or in the next section we talk more about autonomous differential equations and the cool things that we can do with them. And spoiler alert, it's nice because we can go down to 1 dimension. So that's nice and easy. Have a good one. Bye-bye.